So section 11.3 in Young and Freedman's University Physics works out some samples of equilibrium problems to help apply the idea of both torque forces and normal forces, as it were, being in equilibrium. Three samples. So first of all, there's a weight distribution on a car sample. Where is the center of gravity on a car? There's a ladder up against a wall sample that involves the coefficient of friction to keep the ladder from sliding. And then there's a example that has to do with equilibrium, holding a barbell, holding a weight that involves tendons. It's a physiology problem using, again, torque and other forces in equilibrium. But rather than just rework one of the examples from the book, I thought I'd do a problem from the back. So I picked a pretty easy one because I'm a wimp. I picked number 11. The answer's in the back of the book, so I could double check it to make sure I wasn't leading you astray. But problem 11 is a diving board problem where all of the board is attached 1 meter from the left, as you can see. So there's no attachment at the far left, there's no attachment at the far right. The diving board is only attached 1 meter from the left. It's a 3 meter diving board, and so I've done some simple subtraction here, 1 meter here, and then so there must be 2 meters from the attachment point to the end of the diving board. The diving board itself has evenly distributed weight, and so at the 1.5 meter mark from either direction, we have 280 newtons of weight. That is the diving board. And then the weight of the diver at the end is 500 newtons. And in the picture in the book, there she's about to do a back dive as opposed to my very badly drawn forward dive. Well, we're asked two things. We're asked what the force is at this point of attachment, and we're asked what the force is at the far left end. Going from the answers, they don't seem to have paid close attention to signs on this. It looks like they've treated down as positive. So I've done my own little voodoo, as we'll see. Let's dive in. So what is the force at the far left here? What is the force? Just common sense, it seems to me, that we would expect the force here to be in the opposite direction as the force here, and we would expect the force here to be equal and opposite to the force on this side. Now, I might say that the answer in the back of the book doesn't do the opposite sign of the force, but I'm assuming that they're just being imprecise. So, using this point of attachment as the kind of 0 point, then the weight is going to be 0.5 meters away, because if this is 1.5 meters and this is 1 meter, then that has to be 0.5. So 0.5 meters times 280 newtons plus 2 meters away at the end where the diver is times 500 newton. Multiply that through. Again, I get the impression in the examples that they didn't pay much attention to these meters. I've gone ahead and inserted meters in here according to what makes sense to me, but they didn't largely mention the meters in the samples in this way. But okay, so if I play that math out, I end up with basically there being 1140 newton meters of force, torque as it were, on this side. So then it would make sense that the torque here, the force would be an upward, and therefore I have negative 1140. They only have 1140 newtons in the back of the book, and of course this is negative 1 meters away from the point of attachment. So that's how I got up with that. The number agrees with the answer in the back of the book, although in the back of the book they don't have a sign. Okay, so there's my working out of the force here on the far left. So what about the force at the attachment point, the force here? To do this one, I changed my 0 point because it's very difficult to figure out the force here if you're making that the point of the center of the torque change. So I switched to the end as the reference point, as the 0, and then played it out. So the center is now 1.5 meters in, 1.5, and still 280 newtons. And the diver is now 3 meters at the other end. And so we'll apply that out. Again, I put the meters in my calculation. So we end up with 420 plus 1500 equals 1920 newtons of force on this end. And so then at 1 meter out, I divided by 1 meter to get rid of the meters, and I end up with 1920 force of newtons pushing down at this particular point as a result of this all over here. Well, there you have it, my attempt to do one of the exercises in the back of the book using principles of equilibrium.